My guest today is Doyne Farmer, Director of the Complexity Economics Program at the Institute of New Economic Thinking at the Oxford Martin School, a professor at the Mathematical Institute of Oxford University, and an external professor at the Santa Fe Institute. Doyne is one of the world's foremost complexity economists. In fact, he is the first economist I spoke with on this podcast. He has published dozens of papers, and most recently, a book called Making Sense of Chaos, which is the main topic of today's talk. The book reads very well. It is full of anecdotes and stories on top of a deep exploration of complexity economics. As the title suggests, the book is about chaos. Chaos theory refers to systems whose outcomes are extremely sensitive to initial conditions. Because of this sensitivity, chaotic systems feature seemingly random behaviors from the iteration of a simple rule. Think of it, at least for now, as the butterfly effect. In today's episode, we focus on the relationship between chaos and scaling theory, and more specifically, how chaos can be factored into scaling theory. By the end of this conversation, you will learn about why it might be easier to predict the long-distant future than predicting tomorrow, how Moore's law conflicts with other scaling laws that underpin technological progress, how agent-based modeling can help all scientists and policymakers, how to dominate the world with your theories, and even how to trick casinos. I hope you enjoy the conversation. All right. Okay, so I thought we could divide the conversation in three parts. And the part one is what I would call the chaotic introduction. And so I guess I have to start there. The first question being, what led you to dedicate your career to issues related to complexity economics and eventually to write this book?
Well, it's a bit of a long story, actually. It's, in a sense, my life story, which is in the book. I was always interested in ideas about the universe evolving and what's going to happen going forward in time, inspired by reading science fiction stories, particularly Isaac Asimov's Last Question. So I was always seeking some way to think about these issues already when I was an undergraduate in college. But in the course of when I was a graduate student, I embarked on a project to beat roulette with several of my friends. And that set me thinking about prediction and why is prediction difficult in some cases and easier in others. And when I heard about chaos, I was immediately fascinated and got together with a group of my fellow graduate students, and we co-advised each other, calling ourselves the Dynamical Systems Collective, and wrote some papers and got involved in chaos. But once you're thinking about chaos, it's already a question of, okay, this is how a deterministic system can create disorder. How can a disordered system become ordered? And so we began reading literature on self-organization and discovered cybernetics. So I got very interested in that. But in parallel, I was doing things. I did some work to predict chaotic time series and show that even though chaos places a limit on prediction, if you have simple chaos, it actually allows you to make better predictions than you would with a standard time series model. Then I began studying various things like ice ages and sunspot cycles. And every time I would speak about it, somebody would say, have you tried applying this to the stock market? So finally, that became irresistible. And I left Los Alamos, where I was at the time, and began trying to beat the stock market using mathematical methods together with my childhood friend, Norman Packard. Then once I'd kind of reached the point where it was clear what we were doing worked and met my financial goals and was going back to research, I decided to combine my complex systems background with what I'd learned about financial markets and economics, and where I'd seen that I didn't really believe the mainstream views about how one should go about modeling that world. And it resonated with earlier encounters I'd had in economics. And so starting in 1998, then I really began working on applying complex systems ideas to economics.
Somehow that reminded me of the history of a company called Renaissance, where the founder went, back and forth between full-time academic and the stock market, and maybe trying to explore some of the ideas there, and then coming back to academic to explore, the underlying theories behind. But so I thought maybe before we dive into the substance, I would like the listeners to get a sense of your entrepreneurial spirit. And so, could you tell us about your, what I will call here, the casino endeavor, what you've done back in
Sure.
the days? Although I was concerned whether or not this is legal and whether or not you will get into trouble for telling the stories in the book. But please go ahead.
Well, yeah, it's when we did it, it was legal. That is, um, but let me first explain what we did. The basic idea is a very simple one. A roulette ball spinning on a track is a physical system. So it's a uh, rolling ball on a circular track. So we understand the physics of this reasonably well, although it did make a rather challenging homework problem to solve the equations and get everything right. And it's particularly difficult because roulette wheels are typically tilted. So even a millimeter difference between the two sides of the tracks actually makes a noticeable difference in where the ball falls off. So we had to solve that part too. But so we were able to write down the equations. And the key thing that you need to know is that once the croupier spins the ball, about 15 seconds elapses until the ball actually rolls onto the track. And so that gives time to gather information about initial conditions. So once you know the force, we had a switch in our shoe, and we would click when the ball passed a reference point on the track, click again when it passed it again. Then you knew how long it took to go around, which gives you the velocity. And so you know the position and velocity at a given point in time, you know the forces, you can then predict what the ball will do. Now, it's complicated by the fact that um, once the ball leaves the track, there are little diamonds on the track that it can bounce off of. There also are um, frets, divisions between the cups that it can bounce off of. So there are a lot of things that can really randomize where the ball is going. But at least on the roulette wheels that were used at the time and the balls that were used, the bouncing around was not so chaotic as to completely get rid of, if you had the knowledge of where the ball would exit the track, there was still a shadow on the other side of the track that it was very unlikely to land on. So meaning you had better than even odds if you bet on the right numbers. So that was the basis of our system. I should have also said the other key piece of information is that they don't close the bets until typically a couple of seconds before the ball actually exits. So that gives you a window of time to measure the initial conditions and place bets. And in our system, we had two people, one who actually looked very carefully at the wheel and did all the clicking and ran the predictions. And the prediction computer would send a message to another computer that would just send a signal to the bettor about where the ball was going to land. So they knew they would have to then memorize a pattern about which numbers to bet on, depending on which part of the wheel the ball was likely to land in. So we did this for, well, several years. We made 11 trips to Nevada during that time. We suffered a lot of hardware problems. You know, we were not only the first to build a wearable computer, we were the first to build a concealable computer.
Yeah.
So we jumped far ahead of the state of the art. An embarrassing story during that period is while I was working on the program for the computer, one of the other members of the Dynamical Systems Collective, Jim Crutchfield, came back from a meeting of the Homebrew Computer Club and said, hey, there's these two guys at the Homebrew Computer Club that said they were going to sell computers to housewives. We went, housewives? What are housewives going to do with computers? Well, the two people were Steve Jobs and Steve Wozniak. And at the time, we laughed. We thought we're going to make more money on roulette than they're going to make selling computers to housewives.
Yeah,
But we were wrong about
almost.
that. Yeah.
Well, that's a good story. And so, talking about prediction, actually, and moving now into the substance a little bit more, I'm interested in the fundamental limit of chaos theory for short-term prediction, whereas there is no such limit for long-term prediction. And actually, in the book, you give an example. You say, well, it's very hard to say whether it will rain in 100 days from now, but we can estimate whether the global temperature will go up and down in 50 years, given the carbon emission. So, in a sense, what is chaos and how powerful is it?
So chaos is a mechanism in dynamical systems whereby you have sensitive dependence on initial conditions. That is, if you start with 2 points or two initial conditions that are very close together, because they separate exponentially, they will, within some finite time, become randomly scattered over the system. Any precision of measurement that you make, as long as that precision is finite, and it always is, there is some time at which that prediction becomes impossible because points are effectively random. Now, that said, when I say prediction, I mean detailed prediction about where that point will actually be. Statistical prediction remains possible because in the typical case, there's an attractor that things stay on. So points don't just fly off to infinity. They stay within some region, and that region has statistical properties. The attractor has statistical properties. So back to your question, if you predict the weather, you'll notice that predicting an hour ahead is very accurate. Predicting a day ahead is a little less accurate. Predicting a week ahead is not very accurate. And past 2 weeks, there's not much predictability. But if we want to understand something that involves the statistical properties, not whether it's going to rain on a specific day, but how likely is it to rain that time of year, you can still make that kind of prediction even when the system's chaotic.
Indeed. And if you live in Amsterdam, you could predict that it will rain and you'll be right.
Yeah, that's true.
So now moving on to part 2 of the discussion, and here focusing more on the scaling laws. You do explain that chaos looks at endogenous change within a complex adaptive system. Now, most of the listeners will be familiar with the concept, but you make an important distinction that you already alluded to in our conversation between simple and complicated chaos. And you explain that the more complicated, meaning the more chaos is explained by many variables, the harder it is to actually predict. So, what is the basic relationship between complicated chaos and scaling laws? Or put differently, are there no or fewer scaling laws in complicated chaos?
Well, complicated chaos still has scaling laws. So chaos per se doesn't say that you can't have scaling laws operating. And one of the first scaling laws is that the one that we were already talking about, namely, how accurately can you predict as a function of how far into the future you try to predict? The answer is that the prediction horizon, the accuracy of the prediction, decreases linearly when you measure it in terms of bits of information in time. And so that's an important scaling law. That's why largest Lyapunov exponent's an important aspect of the weather. So your accuracy is decaying as you go forward in time. Now, weather is an example of a more general phenomenon called turbulence, fluid turbulence. And turbulence has many scaling laws associated with it. There's scaling laws about how information cascades through length scales and time scales, and how much energy is contained in movements of different frequencies. And so there's a long list of scaling laws for turbulence that were discovered during the 20th century.
So, regardless whether we are dealing with simple or complicated chaos, this has no direct impact as to our ability to uncover those scaling laws or to observe them.
No, that the you can have scaling laws in either system, and in a sense, complicated chaos, I would say, is generally more likely to have scaling laws because uh, there's enough degrees of freedom that things are getting averaged out, and they're less.
Yeah.
Things become less idiosyncratic.
There is
Go
one
ahead.
quote that you give in the book. I forgot who actually coined it when it comes to the butterfly, right? Where it's like, well, if the flap of a wing of a butterfly can change or create a storm somewhere, this may be true, but then you need to factor in the fact that there are millions of butterfly, right? So indeed, it's more complicated in that sense, but it will also average away the result. So my goal with this podcast is to document as many scaling laws as possible and hopefully to discover new ones. And there is, I mean, more than one. The one that you cover in the book, which I found to be fascinating, and I'm here referring to your work on the trophic level, which you define as the depth of an industry supply chain or the number of steps required to produce a product. And you explain that the higher the trophic level, the higher the degree of mechanization, but also the higher the trophic level, the more an industry has other industries below it and can thus benefit from innovation in those industries. Now, as you describe, in addition to Adam Smith's findings that specialization makes the economy work, you found that specialization also increases the rate of innovation in the economy. That seems to me to be a pretty good scaling law. Now, the question is, how robust is it? And if it is robust, what are the policy implications?
I'd say at this point, we don't really know how robust it is. I mean, it was very robust in the paper we wrote. That is, um, it's one of those rare events as a scientist where you make a prediction without even really peeking at the data, and and then you go look in the data, and things were exactly the way we predicted they would be. So we saw this very nice linear scaling with as a function of uh, trophic level, using 14 years of data for the world.
Hmm.
But at a high level, we weren't able to observe this at a really granular level. I think the predictions would work even better if we were able to look at a granular level. But in other words, we were looking at the level of industries, not at the level of firms. But because that's all the data we had. Um, but uh, we predicted that we would see a linear relationship between trophic level and rate of price improvement. And in the 14 years of data we looked at, that linear relationship was almost perfect. So, in that regard, it got off to a robust start. Now, to really test this properly, one would want to look at data from other periods. You would want to look at it at a granular level as well as at a firm level. It should work even better at a granular level, but it's at present not possible to do that. So I guess the answer is we don't really know yet, other than preliminary indications are very good.
But so let's assume that it is robust, right? That you do the
Yeah.
test and you find that, well, that's a thing. And, there are very little variations. Do you think it would work in a top-down fashion? Do you think a government could just, move the industry in a way to specialize all of the companies so that to get more innovation? Or is it more of an emergent phenomenon?
I think it's more of an emergent phenomenon. We're actually moving towards more and larger service sectors, and service sectors have low trophic levels. So, we may just have a slower improving economy
Yeah.
than we've had in the past. And I think that's okay. We don't need to keep improving at the breakneck breakneck pace we've been improving so far. I think we will see things continue to improve and probably see even deeper trophic levels through time than we have now, though we will still see a robust service sector as well. I mean, and maybe let me say the other side. It is possible that things like the IRA in the United States, we recently passed the Inflation Reduction Act, which is really a renewable energy promotion act
Hmm.
that's trying to, among other things, bring manufacturing capability for energy back into the United States. Similarly, the CHIPS Act is supposed to do that. Now, that may actually accelerate GDP in the US because industries in the US will increase their trophic level because we will have more manufacturing, and manufacturing industries have higher trophic level than service industries. So I
Yeah.
think, in the sense you said, yes, a government through industrial policy could increase their trophic level and therefore grow faster.
Yeah, which brings me to technology. You've mentioned services and the CHIPS Act. You talk about the importance of technology in making economies more efficient. You give one example that I liked very much, the one of Google Maps. You say, well, this is a good example of a technology helping to make transportation more efficient by better allocating traffic. So, if technology plays such an important role, and here I quote you, if technology is indeed the single most important driver of economic growth, end of quote, it seems fair to focus on technology a little bit. And here, you actually devote at least one chapter to it, and you talk about Moore's law, which I'm sure all listeners will be familiar with, but also Wright's law, which says that if you double the production of a given product, the cost of production goes down by X percent. And in the case of airplane production, every time you double production, the costs of production will go down by 20%. So please tell us more about the research you did on Moore's law and Wright's law, and specifically the one where you made prediction about 6,000 predictions actually for about 62 different technologies.
Theodore Wright made his prediction in 1936. It's a very interesting guy who was the brother of Sewell Wright, who's one of the great evolutionary biologists. Another brother was Percival Wright, who was considered one of the founders of uh, political science. And but he was the black sheep who became a flying ace in World War One, and then went into the aviation business. And he wrote one paper, but it's a very influential paper where he pointed out the fact that you just said. Originally, he pointed that he viewed it as a fact for a specific factory making a specific kind of airplane.
Hmm.
And but but we've seen now that it actually applies globally, but it only applies to some technologies. It applies to technologies. So it's not clear exactly what, but tends to be technologies that are modular, things that are manufactured, transistors, and computers more generally. It applies to solar photovoltaic cells. It applies to windmills, though at a less rapid rate of improvement. But there's a lot of things, like things we mine out of the ground, that it does not apply to. Take anything we mine out of the ground, it costs about the same now as it did a century ago, within a factor of 5. It's the same. Some have gone up, some have gone down,
Hmm.
but there's no overall dramatic change. Whereas transistors now are a billion times cheaper than they were in 1965 when Moore made his famous prediction.
Yeah.
Solar photovoltaic cells are a factor of 10,000 cheaper than they were when they were first used in the Vanguard satellite in 1958. Whereas oil and natural gas and coal cost about what they did a century ago.
And
So
nuclear power is more expensive,
and
as you
nuclear
explained.
power got more expensive.
Yeah.
Yeah. So I think one of the main lessons to realize is there's a huge difference in the rate at which different technologies improve.
Hmm.
And one of the main drivers of economic growth is essentially the search for better technologies to replace old technologies with new technologies. For example, we've seen that happen in my lifetime for photography. which used to be an industry that was about chemistry and film, and now it's about solid state physics.
Mm.
And it was because solid state devices, be they electronic or photosensors, improving or have been improving at 40% per year for a long time. So they basically overtook the chemical processes that had previously been used for photography and have become now completely dominant.
And to complicate the story a little bit, you do mention the fact that Moore's law and Wright's law are in contradiction to some degree. Moore's law tells you that the costs will go down at a certain rate no matter what, while Wright's law tells you that the cost will go down with effort slash production. So how do you reconcile those two laws?
It's a bit subtle because, just to add to the complexity, the difficulty of unraveling this or understanding this, in fact, when you make predictions with data, at least on the data set that we were able to gather, which was a highly incomplete data set. We actually gathered the data by my postdoc, Bela Naj, organized a couple of high school students and a college undergraduate to go out and gather data out of books. And he wrote to Gordon Moore, Gordon Moore sent back the data he had personally collected on transistors and electronic devices. So we had a very idiosyncratic data set with the order of 100 technologies. In the end, about 60 were good enough to be usable. And then we used those to actually test the ability of different laws, like Moore's law and Wright's law, to make predictions by pretending to be in the past and then predicting forward from the point where we were pretending into the future to see how good those predictions were. So what we saw is that Moore's law and Wright's law had about the same predictive capability. Now, it turns out that you can show easily that if the amount of the technology that you're producing is growing exponentially and the cost is dropping exponentially, then you see Wright's law. So it was on that data impossible to distinguish the two laws. So that led to a quest to find situations where we could distinguish them. We got I mean, Francois Lafond, Diana Greenwald, and I got data from World War II. Diana collected the data. Francois analyzed it. I gave some advice. We were able to show that at least half of the change seemed to be causally driven by Wright's law, meaning, and let me actually throw out yet another question to worry about here, which is, are costs going down because production is going up, or is production going up because costs are going down?
Yep.
That is, if costs go down, then the product becomes cheaper, more people will buy it, or there will be higher demand, and therefore production will go up. So to try and distinguish that, we got the World War II data where we knew that, Roosevelt didn't say, oh, we're going to build more tanks because they're cheap. He said, we're going to build as many tanks as we need to beat the enemy. So, and there we saw that about half seemed to be attributed to Wright's law. Now, the other half was a general exponential trend. Things improved across the board during World War II. And in a way that both can be right or correct. That is, Wright's law is about the specific effort you put into a given thing, but improvements can come from other places. Story that Chris McGee likes to tell, one of my colleagues who also thinks about this a lot and who was the head of research at Ford Motors for some time, is imagine if the engineers at Ford Motors fell asleep in 1975 and woke up in 1995, like Rip Van Winkle did in, U.S. mythology. What would they have discovered? So imagine that cars didn't make any improvements. They would wake up and they'd go, oh my God, there are these new things called microprocessors. I think we can use these to make cars better. Modern cars are full of microprocessors that can do all of the sophisticated calculations much better than the simple analog mechanical computers that were in there before. So the moral of the story is you inherit improvements from other parts of the economy that can be very different In 1975, there were essentially no electronics in cars other than the radio. So Moore's law is more about that. There's a certain amount of technological improvement that happens inexorably. And Wright's law is about how the effort you put into a given technology affects that technology. Now, the extent to which one or the other is true is still not well understood. I should mention, by the way, this connects to the other scaling law you mentioned, though, because one of the things James McNerney showed in the paper about trophic levels in the economy is that at the industry level, about 65% of the improvements in an industry are inherited from the industries that are its inputs.
Yep.
And the Moore's law part, like the story about microprocessors and automobiles, is inheriting improvements sort of out of the blue from some other part of the economy that's not even directly connected in terms of inputs.
Indeed, I was about to say, if you have a standalone product, then you are less likely to benefit from these innovations in chips and microprocessors. Let's move on now to part 3 of the conversation, focusing a little bit more on complexity economics, so taking a step back in a sense. You devote a chapter to agent-based modeling, so which I would argue is kind of the microscope that complexity economists are using, right? The tool. And in fact, several of your articles are deploying agent-based modeling. Now, as you know, but I point this out for some of our listeners, ABM has scaling challenges because it represents non-linear phenomena. And specifically, if you double, for example, the number of agents in the simulation, your ABM will not necessarily reveal the same dynamics. So in a sense, ABM can be limited. Now, there is a recent drop in the cost of computing, which is mitigating this problem. So, and I would argue this is a big reason why there is a clear momentum in favor of ABM and complexity economics. The question is, how big is the momentum? Or to put it differently, what can you simulate today that you could not simulate, let's say, just 5 years ago?
Yeah, well, I think it's better to think on even longer timescales. I mean, computing has been steadily getting better following Moore's law, the factor of billion better since Moore made his prediction.
Hmm.
So that's a big number. Now, Moore in 1965 was about the same time as Herbert Simon, who was in a sense the prophet of complexity economics. So when Herb Simon was laying out the vision in circa 1965, the computing power we had was 1/billionth what it is now. Now, better computing power translates into lots of other things as well. It translates into more data because it means it becomes much easier to gather data and store it, because part of computing power improving is that memory has gotten cheaper at roughly the same rate, maybe a little faster than the computational unit itself. So we have more data. More data means we can understand more about what people do, because economics is ultimately about people. So we're making improvements in all 3 of those domains at once. And that is coming together, not suddenly, but steadily. We've had steady improvement over now a long span of time. Now, meanwhile, economics got focused in a different direction. Economics has focused on utility maximizing models that they do require a lot of computation to compute optima, but they went down that other route. And the wall they hit there is a much harder wall than we don't have a similar wall in complexity economics. That is, as I say in the book, quoting some well-respected economists, optimization calculations can't be done for more than about a dozen variables before they become intractable. And even if you double the computer power, you might move from 12 to 13, but you're not increasing even linearly with the number of variables. Whereas in agent-based modeling, with twice the computer power, we can do things for twice the agents we had before. So we're getting linear improvement with something that's exponentially improving. So that means we've been getting a lot of improvement. Now, meanwhile, the economists have been mostly distracted doing something else. So I think growth in complexity economics has been slower than it should have been, because there haven't been that many people doing it. You have to essentially um, resign yourself to being labeled a heretic and not being able to publish in top journals, because
Mm.
agent-based models are not considered an appropriate thing for an economist to do, because you don't have as much opportunity to show off your math skills. And so I would say progress has been much slower than it could have been, simply because the mainstream community was devoting its attention elsewhere.
Yeah.
I think that will start to change, because um, the situation's becoming ripe, and we're seeing breakthroughs where we're doing better, noticeably better than mainstream models, at least on smaller scales that we're working on.
Well, on this idea of agent-based models not being proper, this is also something that I see in the legal literature. Um, it is not something that, as a legal scholar, you are expected to do. And in fact, I've done some research on the subject, and you see that agent-based modeling is rarely mentioned in the legal literature, even in the business law slash economic law literature, where economic theory will obviously play a more important role. But what you find in even smaller quantities are papers deploying agent-based modeling to legal subjects, right? But regardless of that trend, John Schuler and I, my co-author, decided a couple of months ago to deploy an agent-based modeling where we have agents looking for information on the web using a search engine. And we've put them on a scale where some of them are very sensible to privacy, others are not. They only are sensible to the quality of the search results. And what you can do is here to introduce regulation. So some would be privacy regulation, some others will be market friendly regulation, where you see that the data could come and go from one search to the other. In any case, what we found is that although obviously you cannot simulate the state of the world, but what you can do with agent based modeling deployed to legal scholarship is to get a better sense as to what is the best timing of regulation. Because what we show is that if you introduce privacy regulation before you introduce a market regulation, you do not end up in the same state as if you did the exact opposite, right? But I will come back to this issue toward the end of our discussion. But for now, coming back to your book, you say, and here I quote, that in the past 5 years or so, complexity economics transitioned from a qualitative to a quantitative science, and we are in the process of moving from a conceptual to a practical phase of model deployment. Now, my question is this: do we want to make complexity economics entirely quantitative? And I could see how this will help acceptance amongst economists, but don't we lose something important, something that is inherently non quantifiable? And the reason for my question is a paper of George Akerlof entitled Sins of Omission and the Practice of Economics, in which he argued that economists have a tendency to reward what he calls hard propositions, meaning propositions that can be quantified. And in his views, it's of course necessary, but doing only that then misses the point of the soft propositions, the things that cannot be quantified. So, what's your take on that?
Well, I agree with Akerlof, and I think there's plenty of room for both. My book has ABMs ranging from very simple ones, where that are designed to illustrate a conceptual point, to much more complicated ones that are really trying to be more realistic and make quantitative predictions. So I think there's plenty of room for both kinds of things. I think that in terms of gaining acceptance in mainstream economics, the quantitative part is essential,
Yep.
simply because we can do much stronger tests. If once a model is really quantitative, you can get much more evidence about whether it's right or wrong. And at least you can make strongly falsifiable predictions.
Yeah.
So if you try hard to falsify those predictions and you can't, then you start to feel like the model must be, at least in some sense, approximately right. And economics has been short on such things. There are a lot of Nobel Prizes have been given for work that, with hindsight, is just wrong, because the criteria of empirical verifiability have
Mm.
not been imposed for the economics Nobel Prize the way they are in chemistry, physics, or physiology and medicine. Um, so, so I think it's a good thing to make more quantitative models, but that doesn't say we can't continue to make qualitative models and do conceptual things that are not easily empirically verifiable.
That reminds me, actually, talking about the Nobel Prize, of the lecture that Friedrich Hayek gave when he received the prize, in which he mentions complex systems quite a few times. What's your take on that?
Certainly, some of Hayek's ideas were very much complex systems ideas. The
Yeah.
idea, in particular, that the economy is self-organizing, and so um, it finds the right way to allocate resources through prices and supply and demand, and it does so that effectively enables parallel processing of information. So those are very complex systemsy ideas, I would say.
Yeah. All right. Let me ask a final question, which relates to world domination. Um, what will it take for complexity economics to scale and perhaps one day dominate other approaches to economics? You do explain that complexity economics modifies or replaces all three pillars of neoclassical economics, namely utility maximization, equilibrium, and agent belief. And by comparison, you do also mention that behavioral economics only challenges one of those pillars, agent belief, and yet is not mainstream. So, how can we ensure that indeed complexity economics in, let's say, 30 years from now will be the dominant approach?
Well, uh, what becomes dominant, of course, depends on what people think. I mean, we tend to think of science as an objective thing. And it's true that the science itself is objective, but the way it's done is done by people. So people are going to have to change their views. So I don't think we can guarantee anything. But I do think that in 30 years, we are certainly going to have quantitative agent-based models for the economy that are going to become the standard for predicting lots of things. Now, whether the people that do that will sit in economics departments or in economic engineering departments, or they'll be given perhaps some other name, and then we'll have those departments competing, I don't know. But I think it's inevitable that within 30 years we're going to have this. I think it may even be already in 10 years, we're
Mm.
going to see that agent-based modeling will start to become, uh, if not dominant, will be seriously challenging mainstream, and for lots of purposes will become the standard tool.
And I mean, what role would you play? I guess, what are you working on nowadays, now that the book is finished?
Yeah. Well, I've started a company called Macrocosm, and our company is devoted to scaling up ideas from complexity economics and reducing them to practice.
Mm.
So, among other things, agent-based modeling. So, we're using the agent-based model that we built for the COVID pandemic, uh, for understanding the economic consequences of the COVID pandemic, where we were very successful in predicting how it would affect GDP. Um, we're using that more generally for disasters and thinking about supply chain risk and questions like that. We're building an agent-based model of the power and energy sectors, where we model firms at the level of individual firms. And we are confronting the scaling problem that you mentioned ago, that if you can't simulate at one-to-one scale, you
Yeah.
have to make sure that you're doing things, you're scaling your model appropriately to
Yeah.
capture the things you hope to capture as well as you can. Now, I think eventually we'll be able to run these models at one-to-one scale.
Mm.
And It just takes a large computing budget to do it.
Yeah, which will
But
decrease over years.
no, the computing budget goes down as our company gets bigger and our budget gets bigger. Our budget will go up, and we will reach the point where we can simulate the whole global economy at 1-to-1 scale. That doesn't mean we're simulating every explicit individual. We want to preserve everybody's confidentiality.
Hmm.
Though I would hope to simulate firms as much as possible at 1-to-1 scale. I think, frankly, that's okay.
Yeah. All right. Well, in the meantime, the book is not yet public, but will be by the time I put out this episode out there. So congratulations on writing such an interesting and also entertaining book with many stories and great insights. I deeply enjoyed reading the book. Thank you for your work. And to everyone out there, take care of yourself. And if you can, someone else too. Bye-bye.
Thank you.